Alright class, let's keep talking about gases. Now, what I'm going to talk about right now, I'm going to talk about collecting gases. Here's the deal. The deal is because gases have a small density, it's not very practical to collect them. But one way to do it is that if a gas is insoluble in water, we can collect it over water. So we can collect gases over water. And over water is the key word to look for. Okay? Now sometimes when a gas is produced in a chemical reaction, we can collect the gas by water displacement. For example, let's say we have this reaction going on. We have Mg plus H2O. If you have Mg plus H2O, the product would be magnesium hydroxide plus H2 gas. Okay? So H2 gas is going to be a product. So if a gas is produced in a chemical reaction, in a chemical equation, we can collect them by water displacement. We can collect them by water displacement. And you've done water displacement before. So let's go over what I mean by that. So we can collect this gas by water displacement. We can collect the gas by water displacement. Now check this out, okay? So over here, I have water and I'm going to have magnesium in here also. So this reaction is happening. As this reaction is happening, H2 is produced in this chemical reaction. Now, because H2 is produced in this chemical reaction, H2 is insoluble in water, I'm going to have H2 gas here. Now what happens is over time, as more and more and more H2 is producing, is going to do water displacement. The volume of water is going to go down and more of the H2 gases is going to be formed over here. Okay, so again, a gas is produced in a chemical reaction. You can collect it by water displacement over water. Yeah? Okay, perfect. Except there is one tiny problem. So the green, these are H2 gas. Here's the problem. Let's say I want you to try something out. Go get a glass of water and mark the volume of the water in your glass. Leave it outside for me for a couple days. In a couple days, when you go back to the glass of water, you will see that the volume of water has come down. The volume goes down. Try that. It will be really cool. Do a little experiment. So the volume of water goes down. Why is that? Here's why. What happens is when you have water liquid, over time, some of the water liquid are going to get enough energy to go to the gas phase, okay? So over time, some of the water liquid will get enough energy, even at room temperature, to go to the gas phase. So this is a little bit convoluted. We are forming H2 gas. I'm collecting H2 gas over water, but because it's over water, the other thing that I have to care about, that every time you collect something over water, you will also have some H2O vapor. You will also have some H2O vapor in there. You will also have some H2O vapor in there. I will also have some H2O gas in there. So it's not just pure H2 that I'm collecting H2 gas and I'm collecting H2O gas. So far so good. Okay, hopefully the concept makes sense. Now let's do a practice problem. Here is our practice problem. Now when you read this practice problem, the keyword that I want you to pay attention to, don't even read the entire question, just skim it. When you skim this question, you go, ooh, collected over water. And we said that's very key. So anything that is collected over water, that's going to be key. Okay? Now, read this problem. When you read this problem, you can probably tell me, is this a changing problem? No. not a changing problem because nothing is really changing, right? So if it's not a changing problem, what that means is this is going to be a straight up PV and RT, right? Okay, you know how to do this. I'm going to write down PV and RT because it's not a changing problem. And what are we looking for? What is the variable we're looking for? What we are looking for is volume, right? They ask you what is volume, okay? So I'm going to isolate volume and RT over P. That's perfect. Now I'm going to plug in numbers. The first number I have to plug in is moles. Okay. Now remember, we're looking at the volume of H2. We're looking at the volume of H2. I know this sounds crazy, but I have to repeat this every time. Don't forget, ideal gas law is for gases. Ideal gas law is for gases, right? So what I'm looking for here is the volume of H2 gas. Okay. Well, I don't have the moles of H2 gas, but what do I have that could help me out? I have the grams of Fe. That's good enough, right? Yeah, because you know how to do this. So if you have the grams of Fe, you can convert that to moles of H2. Remember that from previous chapter. Every time they give you one thing, they give me the kilograms of Fe. But what I need is moles of H2. When they give you one thing, but they ask for something else, you have to use hashtag mole ratio. It gets a hashtag because it's very important. So every time they give you one thing, they ask for something else, you have to use hashtag mole ratio. I have to use a mole ratio here. Now, because I need to use mole ratio, I need to convert it to moles. So I'm going to write down what's given to me, which is 1.00 kilograms of Fe. Okay. Do you like kilograms? No, you probably don't, right? What do we like? We like grams because molecular weight is moles per gram. So I don't like kilograms, goes down here, grams goes on top. This is great because now I can cancel out kilograms. What's the conversion between kilograms and grams? Remember, kilograms is a larger unit. So you always put a 1 next to a larger unit. 1 kilogram is 1,000 grams. Okay. Again, grams I don't want. I'm trying to get to moles so I can do a mole ratio. How do I convert gram to moles? You know that. Molecular weight. Gram comes here. Mole goes on top. 1 mole of Fe is 55.8 grams. So now I converted gram to moles using molecular weight, but Fe is not what I want. What I want is H2, so I have to use hashtag mole ratio. So mole of Fe goes here, moles of H2 goes on top, so I can cancel out the moles of Fe and I end up with moles of H2. Now, how do I find out the mole ratio? Coefficients or the mole ratio. Coefficients or the mole ratio. Coefficients or the mole ratio. Don't forget that. So I have 4H2 for 3 Fe. Okay, so it will be 3 over here and it will be 4 over there. Perfect. Now everything is good. Now what you're going to do when you multiply everything on top, divide by the bottom, what you get is 23.9 moles of H2. Okay, that's what I want. So I have moles of H2. I'm going to come up here. So I have that. That is great. So I'm going to plug it in. So what I have over here, I have 23.9 moles of H2. You guys are good? Okay. Now, R is an ideal constant, 0.08206. Okay. Do I have a temperature? Temperature is given to you here. What is the temperature? Is 30 degrees Celsius, but don't forget you have to add 273 Kelvin to it, so it will be the right temperature. Yeah? Okay, so far no good. So far so good. I have the moles, I had the R, I have a T. Let's go to the pressure. They tell you that the external pressure is 700 millimeters of mercury. So the external pressure, which is the same thing as the total pressure, is 700.0 millimeters of mercury. If this problem was not over water, you would be done. Except this problem is happening over water. When it's over water, what do you have to consider? So this problem is over water. Because it's over water, what do you have to consider? Every time you're collecting gas over water, you have to consider H2O gas. Because we said it's not just the gas that you're collecting, it's also some H2O gas that is going to get in there. So this 700 millimeters of mercury that they give you is technically is the pressure of H2 gas plus pressure of H2O gas. Because you don't just have H2 in there, you guys going to be convoluted with H2O also. We're good so far? Okay. So how could you just get H2? Because all you want is just H2. So you have a total is 700 is H2 plus H2O. Okay. Now read this problem. They tell you that the vapor pressure of water at 30 degrees is 31.8 millimeters of mercury. Okay. So that means is the 700 millimeters of mercury is equal the pressure of H2 plus the pressure of H2O, which is 31.8. Okay, you guys are still following me? Beautiful. Okay, now what am I going to do? So I would have to subtract those two to be able to get that number. 700 minus 31.8. That's going to be 668.2. I don't like doing math in my head. Millimeters of mercury. Okay, so I have that. Now again, don't forget the units really matter. So I'm going to come over here. So I have 660. Let me write it a little bit nicer. 668.2 millimeters of mercury. But what do I have to use? I have to convert it to ATM. 1 ATM is 760 millimeters of mercury. Okay, perfect. If I plug everything in, what I end up getting is, I'm going to end up, hopefully you get the same answer as me, 676 liters. Because this equation gives you liters. Yeah? Okay. Not bad. Good question. We did a PV and RT question and you just plug it in. Don't forget the units as always. The only thing that made this problem hard is that collecting over the water. And every time you're collecting over the water, what you have to care about is that don't forget that there is a H2O gas in there too and you have to subtract it. Look at this again to make sure you understand it. We did subtract it because we knew how much H2O was there. And again, this number, I look it up and there's a table. There are many tables that tell you what is the vapor pressure of water at different temperatures. All right, beautiful. Really nice job. Let's move on to the next part. So gases are moving around rapidly. Do you agree? Because gases are moving around rapidly. Anything that moves around rapidly, you need to consider velocity, right? We need to consider velocity because gases are moving around rapidly. And, I don't like using the word velocity because it sounds so fancy, but it's really not. Velocity just means speed, right? Velocity means speed. Now, for gases, when talking about velocity, the root mean square of velocity. So we're going to talk about root mean square of velocity, which would be So root mean square of gases, and you guys know what this line means? That line means average. Every time you see that line on top, that means average. Okay. Now I'm going to give you the equation. The root mean square velocity for gases. Here's the equation. 3RT over molecular weight. 3RT over molecular weight. Okay. This is the equation. I want you to put a little line square around it. 3RT over molecular weight. Now let's go over this together. Okay. T is temperature. It has to be in Kelvin. Don't forget. MW is molecular weight. It's going to be in kilograms per mole. Okay. And R is a constant, but it has a slightly different unit. So it's 8.314 joules over Kelvin mole. Okay. Now again, we used to 0.08206. That has a different unit. Now we need joules Kelvin mole. So 8.314. This is the constant you use for velocity of gases. Okay. Now you already knew this. I promise you already knew this. Because what happens when gases have a high molecular weight? If you have a high molecular weight, what do you think is going to happen? We talked about this. If you're a heavy gas, if you're a heavy atom, can you run around fast? No, you probably can't, right? Most of the, like I said, elements, atoms are like human beings, right? If you're lighter, we can run around faster. If you're bigger, we can't run around as fast. Exactly the same idea here. Now, I'm going to look at this from this perspective. Here, if you look at this, if the molecular weight comes down, that means the velocity goes up. So if you're a lighter gas, you're going to have a high velocity. You're going to run around faster. If this goes up, the velocity is going to come down. So far, so good. Okay. So don't forget, if the molecular weight comes down, that means the velocity is going to go up. And the other way around, molecular weight goes up, the velocity comes down. High molecular weight, you can't really run around fast. So far, so good. Okay, so gases, we have to care about velocity because they're running around fast in the room right now. Now, next one we're going to talk about. We're going to talk about Graham's law of diffusion and effusion. Diffusion and effusion. Again, you already know this. I promise you already know this. We talked about this, things diffusing, right? So diffusion and effusion. Let's go over what these means. Diffusion is a process of gases filling the box, okay? Let's say I have helium gas and I have xenon gas. These gases are going to fill up the box. The process of gases filling the box. Now, effusion is a process of gases escaping the box from the hole. The gases are going to find a hole and it's going to escape the box. So these gases are going to escape the box. That's effusion. Okay? All right. Now, I have a question for you. If we have the same temperature, which one do you think is going to fill the room faster? Helium or xenon gas? Which one is going to fill the room faster? The answer is helium. Helium is going to fill the room faster. Why is that? We just talked about it. If you're a lighter atom, if you have a lower molecular weight, that means you can run around faster. If you run around faster, you're going to be able to fill up the box faster. The same as effusion. If you're a lighter atom, you're running around faster. You have a higher chance of finding that hole and getting out of there. So far, so good? Okay. So if it's same temperature, the lighter atom, the lighter gas is going to fill up the room faster. We're good? Okay. Now, so we have two gases here, and we decided the one with the lower molecular weight is going to fill up the room faster. Now, we're actually going to put equation to this, right? If you're comparing two gases, here we're comparing xenon and helium. If you're comparing two gases, that means rate 1 over rate 2 equals molecular weight 2 over molecular weight 1. Now, before you get confused, and I will explain this, let's put a box around this. Do you remember that when we talked about velocity, and we just did that, when we talked about velocity, we said the velocity of gases is 3 RT over molecular weight, yes? We said the velocity of gases is 3 RT over molecular weight. Now, I said we have a same temperature. If you're in the same room, that means you are going to have the same temperature, right? If both gases are in the same room, that means you're going to have the same temperature. So that means the temperature goes away and R is a constant, so this will go away. So now when we compare two gases, the only thing that matters is the molecular weight. We're not in the same room. So if you're in the same room, that means you have the same temperature. So now when you're comparing gases, the only thing that matters is the molecular weight. So comparing the molecular weight will tell you which one is going to fill up the room faster, which one is going to have a faster diffusion or effusion. We're good? Beautiful. Let's do a practice problem to see how we use this. Okay, so when you read this question, we have two gases, right? We have the H2 gas and we have a HF gas. And then they're asking you how many times faster or slower will H2 pass through a pinhole than HF. Let's answer this conceptually first. Which one is going to be faster, H2 or HF? What do you think? Tell someone next to you. Your roommate, your housemate, your sibling, if you can find someone, tell them right now, which one is going to be faster? Hopefully you said the right answer, which is H2. H2 is going to be faster. Why is H2 going to be faster? Because it has a lower molecular weight. The smaller atom, the lighter atom is going to run around faster. So it can find a hole and get out of the room or fill up the room faster. So far, so good? Okay. So conceptually, we're good. This was conceptually. Conceptually, we're great. We know H2 is going to be faster. But it asks us, well, how much faster? To do that, you know the equation. Molecular weight 2 over molecular weight 1 is going to give you the ratio. Now, if you wanted a ratio to know how much faster is the lighter guy is going to be, what you're going to do, put the heavier molecular weight on top. So put the heavier molecular weight on top. If you do that, then you get a ratio that's going to tell you how many times faster is the lighter atom or it's going to be. So far, so good? Okay. Now, what is the molecular weight of HF? That's my heavier atom. That's my heavier molecule. Okay, look it up. The molecular weight would be 20. The molecular weight of H2 is 2. If I take a square root of that, it would be 3.2. So what does that mean? That means H2 is 3.2 times faster than HF. And as long as you put the heavier atom on top, then you get a ratio that tells you how many times faster is the lighter atom is going to be. Yeah, so far so good. Beautiful. Now I'm actually going to give you a take-home problem, yeah? Even though you're home right now, it would be still a take-home problem, stay-at-home problem. Alright, do this problem, and I'm about to put, and the next time, the first time before I start the lecture, I'm gonna do it. I'm gonna review the problem. All right, here is a take-home problem. Right? Do me a favor, do this take-home problem. Spend some time on it. do the second problem, and the first thing we're going to do next time, we are going to review this. I will see you next time. Do the second problem.